Today you're going to use a normal model to calculate binomial probabilities. Okay, so suppose the Tennessee Red Cross anticipates the need for at least 1,850 units of O-negative blood this year. It estimates that it will collect blood from 32,000 donors. How great is the risk that they will fall short of meeting their need? Remember, our N is 32,000 and our probability is 0.06. Because remember in the previous lesson for binomial models, we said that 6% were universal donors. So to set this up with a binomial, because it supports bins, remember we have two outcomes, they're either O negative or they aren't. The probability of success is constant, right? That's the S, that is 0.06. Individuals should be independent of each other. That's the I, and then the number of fixed trials is 32,000. So to set this up, this is what here is what our formula would look like. And remember, to do this in the calculator, we want to do a binomial CDF or binomial PDF. But we can actually type this into our calculator. Now, remember that fraction bar should not be there. Right, this is 32,000, choose 1,850. In other words, you're going to use the NCR. So remember, when we do 32,000, choose 1,850, we might get an error. Meaning we might get this error overflow message on our calculator. Meaning the calculator exceeds the range of values for this machine is able to display. Notice, and then it would say error. So what do? Well, when we deal with such large numbers, calculations become tedious or impossible. For example, we conclude that the mean, or mu, and the standard deviation of sigma. If we approximate the distribution with a normal model, we can calculate our probability. Okay, so remember in a binomial model, to find the mean, you take the n times the p. Okay, so we'll take our 32,000 times 0.06. And it should give you about 1,920. Remember to find the standard deviation. That is the square root of NPQ. So in other words, we're going to do the square root of 32,000 times 0.06, probability of success, times the probability of failure, which is 94%. And then square root all that. And we do get about 42.48. Okay, now once we do that, we can set up our probability statement and we find a z-score. Remember, it is helpful, it is helpful to draw a picture, right? And if you have a normal model of 1,920 with our standard deviation, and a z-score of negative 1.65, just somewhere over here. You can either use the chart or you can use normal CDF. It is about 5%. Okay? Let's look at another example. The communications monitoring company Postini reported that 91% of emails are spam. Recently, you installed a spam filter. You observe that over the past week, it okayed 151 of 1422 emails you have received, classifying the rest as junk. Should you worry the filter is too aggressive? Meaning, what is the probability that no more than 151 of the 1,422 emails is a real message? Okay, so you might ask yourself, well, is this problem like the previous one where we had a really large sample of people and we wanted a specific number that was also large? Well, we can't always just use a normal model. We have to have at least 10 successes and at least 10 failures, and that will be critical for the next unit also. Okay, so as the number of trials increases, the more normal our models become. A binomial model is approximately normal if we expect at least 10 successes and 10 failures, meaning NP is at least 10 and n times 1 minus p, or n times q, is at least 10. So our first step, we're going to determine if a binomial model is appropriate. And this is where we would use our bins. So remember the B, is it binary? Okay, so it is binary because either the message is spam or it isn't spam. Okay, so next we're going to ask ourselves, are emails independent of each other? Well, they should be. The n, do we have a fixed number of trials, right? We know that 1,422 emails is a finite number. And then finally, is the probability of success constant? Well, the probability that we have a real email is 1 minus the 91%. So in this case, it is 0.09. Okay, so we would say here that a binomial model is appropriate. Okay, so we would say a binomial model is appropriate. But could be difficult to work with. Primarily because that 1,422 emails is a pretty high number. So the next question is, well, can we approximate this with a normal model? Well, remember, in order to do that, the first thing we'll do is we'll check n times p. Okay, so that would be our 1,422 times 0.09. Okay, and that does give us 127.98. Then we have to do our failures. Okay, so we'll do the 1,422 times 0.91, meaning the spam emails. And this is 1,294.02. Now, because both NP and NQ are at least 10, we can use a normal model. So our next step is to find the mean and standard deviation. Okay, so remember the mean. Okay, so the mean, we're going to take n times the number of successes, and we already found that to be 127.98. And to find the standard deviation, you would do the square root of n times p times 1 minus p, or q. So the square root of 1,422 times 9% times 91% is about 10.79. So our next step is to calculate and graph our z-score, find the probability, and then write a statement in context. Okay, so the first thing we'll do is we'll find our z-score, and notice we have our direction and our probability. If we look at our picture, remember there are a few things that we need to include. For example, we need to indicate that this is a normal model with the mean and standard deviation. And we have to be shaded in the appropriate direction, and our shaded region should be about 98%. The last thing for us to do is to write our context. So according to the model, among the 1,422 emails, there's over a 98% chance that no more than 151 of them were real. So the filter seems to work. Okay, so when we talk about continuous random variables, remember a problem arises when approximating a binomial model with a normal model. The binomial model is for discrete cases, whereas a normal model is for continuous random variables. When we use our normal model to approximate, we can only use it for intervals of values rather than the exact values. And here are some other things that could potentially go wrong. Make sure you have Bernoulli trials, meaning you're using the bins to verify I can use a normal to approximate a binomial. Remember, there's only two possible outcomes. A constant probability of success. Is there independence? If it is not independent, does it satisfy the 10% condition, meaning that less than 10% of the population is sampled? Please do not confuse geometric and binomial models. Remember, geometric is you repeat until you have a success, whereas a binomial is count the number of successes in a fixed number of trials. Do not use the normal model with a small n size. Make sure you have to check your success-fail condition, and you should have at least 10 successes and failures. Let's look at a few more examples. Okay, so notice we have the Research Center reports that they are actually able to contact only 76% of the randomly selected households drawn for a phone survey. Explain why these calls can be considered Bernoulli trials. Okay, so these can be considered Bernoulli trials because it is binary. There's either contact or there's not. Calls should be independent. Now, we don't have a fixed number of trials, but remember, Bernoulli trials does not necessarily mean fixed number of trials. That's for a binomial model. And then the probability of contact is 76%. So that brings us to number 2. Which of the models, geometric, binomial, or normal, would you use to make the number of successful contacts from a list of 1,000 sampled households? Okay, so for right now, we're going to say it's binomial because we have that fixed number of trials, 1,000, and our probability of success is 76%. But for those actual calculations, we're going to use a normal model because 1,000 is a pretty large number. And if we wanted to verify everything, we know that the mean would be 760, the standard deviation about 13.506. And we know the number of successes is 760, the number of failures therefore is 240, and both of those are at least 10. So a normal model to approximate the binomial is okay. And then number 3, Pew reports that even after they contacted a household, only 38% agree to be interviewed. So the probability of getting a completed interview for a randomly selected household is only 29%. Which of the models would you use to model the number of households Pew has to call before they get a completed interview? Okay, so this one you would use a geometric because you want to know how many do they have to call before they get a success. So this would be a geometric, and your probability is 0.29. It's an equal sign. And guess what? That's the end.